All right. I kind of went over the different sections that we're doing. It's not super important, but we got relative dating, absolute dating, and then at the end we go through the history of life on Earth. This is, I don't know. It's not my favorite area. I'm not super into biology and stuff, but it's got some interesting stuff in that little section. So today, like I said, we're going to start on the development of Earth, and kind of talk about how that process led to early conditions on Earth. I don't think we're going to do a whole bunch of assignments on this, so I might try to go through this pretty quickly. I don't know that we'll do an exploration on this section, maybe just the regular normal assignments. So we're going to start off at the top here with the structure of Earth. And they say after the planet formed about 4.6 billion years ago, several processes released heat that kept the surface a molten pool. So we talked about the Hadean era, and how at the very beginning of the Earth, it was mostly molten material. It was all volcanoes. There was no water. For a long time, there wasn't even like solid land. It was just really in a molten state, that didn't really allow for anything to form, especially no life, not even rocks. So the young planet was hit by a bunch of materials from space. This is actually in the area of time that the Mars-sized object would have hit Earth and created the debris that eventually became the moon. And so that happened early on in the planet's history. Accretion is a term that describes the addition of material to the planet from space. We also use this term to describe how continents get bigger. Usually, if you look at the history of a continent, the middle part is the oldest and the outside part is the youngest. And so like the land that is California used to not even be part of the continent. At some point in time, this is a bad analogy, but you know how you like scrape mud off your boots on the edge of like concrete or something? That's actually what happens as oceanic plate. Like if you have islands kind of like Hawaii out there, and that oceanic plate gets subducted underneath the continental plate, those islands just kind of get scraped off onto the side. And so they will be pushed onto the continent and kind of join that land, and it just gets bigger and bigger and bigger. And so that's kind of a process that happens on plate tectonics. But when they're talking about it here, they're talking about asteroids, bigger chunks of rock early on in the Earth's history, colliding with it and kind of adding to the size of Earth, giving us more heat, more gravitational compression, and kind of solidifying the Earth a little bit, kind of bringing everything together. Differentiation is basically like gravity taking over. It's going to pull all the heavy stuff down. All the light stuff is going to float to the top. And that's actually what we have now. Your lighter elements like oxygen and silicon and aluminum, those are all up towards the surface making up the crust. Where at the core, you have your heavier metals like iron and nickel, which literally weigh more per atom. And so gravity is going to pull down on them more. They're going to end up in the center of the planet, where your lighter elements, oxygen, silicon, carbon, nitrogen, those are all going to be up towards the surface of the planet. And so that's the differentiation. What they mean is creating those different layers that we see now. The inner core, the outer core, the mantle, and then the thin layer of crust that we live on. They talk about radiogenic isotopes. What they mean by radiogenic is radioactive. So they're not stable. They produce radioactive isotopes. They start to release energy, and they release a little bit of heat as they transition to more stable, less radioactive things. So yesterday we talked about plutonium. I think it was plutonium. Decaying down into lead. Lead's more stable than plutonium is. That's what they're talking about there. And when it does that, it releases a little bit of heat, which kind of added to all the stuff that was going on at the time. So know that we have just a couple elements that make up quite a bit of the Earth. Obviously not everything. We've got pretty much everything here on the periodic table. But as far as percent-wise, it's mostly iron, oxygen, silicon, magnesium, nickel, and sulfur. That's going to be a early kind of mixture of what the Earth was made out of. So early Earth consisted primarily of dense liquid metals liquid iron, liquid nickel. Those are the ones that sank to the center and ended up becoming the core. Your less dense materials like aluminum, silica, rose to the surface and ended up creating the crust that we kind of have at the surface. So let's see. They talk about the molten material separating into 3 layers, which they're probably going to say is the core, the mantle, and the crust. The core is actually separated into 2 different cores, an inner core and an outer core, but we still call it the core. So they talk about the inner core. They talk about the outer core. They give you thicknesses and depths below. Notice that the densities are what matters. Gravity's pulling down on the densest things. The least dense stuff is going to float to the surface. The most dense stuff is going to sink down to the bottom. Make sure you're staying awake. Tap on him. His head's over there leaning. The whole internet now knows that you fell asleep in class. You should feel shame. So the inner core is about 13.5 grams per centimeters. It's the heaviest. So that's why gravity's pulled it down. It's all the way down towards the center. If you go to the outer core, I don't know if they give you that. Here it is. The outer core's density, it doesn't even say. The outer core is going to be less dense. The mantle is going to be less dense than that. And then your lightest material is actually going to be your continental crust versus your oceanic crust. So they talk about the asthenosphere. The mantle is melted. Do we have a picture of all this? Does everybody know what the mantle is in the outer core? That's a video segment. Here we go. Let's look at this image in a new tab so we can all see it. So here you go. Your inner core and outer core are right here in the center. The mantle is going to be this really thick part that separates the core and the crust. The mantle is molten. So it's all melted. It moves. It has convection cycles. There's all sorts of dynamic things going on here. And obviously, the outside crust is not melted. The asthenosphere, which is a weird term, but the asthenosphere is like the transition between those. So it's not quite melted, not quite solid. It moves like a thick plastic or like a thick honey. So it's like almost melted, but not really. That is like the transition zone. And that's actually what allows the continental crust to kind of move around in the plates that we have. So it kind of floats on the asthenosphere and it's allowed to move around the Earth. So they talk about the development of the asthenosphere here. They give you a couple more densities for the mantle. So note that the inner core was like 13.5 grams per centimeter cube. This is 4 and 10 grams per centimeter cube for the mantle in between that.
Wait, how is the inner core solid and the outer core liquid?
So the inner core is solid not because of temperature, but just because of pressure. So it's well hot enough to be liquid. It's just that there's so much stuff pushing on it that the atoms can't move like a liquid. They move like a solid. And actually, maybe when we get into earthquakes, we'll kind of learn about how we know that. Because we've never been down there. We've never drilled down there or anything. And so it's actual earthquakes and a little bit of like nuclear weapons testing that has led us to understand that the inner core is solid. Keep that close. We ain't done yet. Eyes open, computers closed. That's what I'm talking about. Okay. So at the surface, we have the crust. Rocks found on the planet's surface are the crust. Know that the crust is very, very thin. You're really only talking about, 100 to 150 kilometers thick. And the ocean's less than 100 kilometers, so pretty thin there. And the rocks formed on the Earth's surface about 4 billion years ago. Some of the crust is just about that old. The continental pieces are actually pretty old because they don't sink. They don't get recycled. They've kind of just all been hanging around for that long. Obviously, not all the sediments are, and you have to work to find old rocks like that. But they even tell you the oldest rock on the planet was recently discovered along the Hudson Bay in northern Quebec, which is Canada. So they think it's part of the very, very early on crust that we have. Let's see where they go to next. Earth's early atmosphere. The early atmosphere was not like the atmosphere that we have today. If you, did I say this the other day? If you went back in time, you'd not be able to breathe the atmosphere. Yeah. And so it's quite a bit different. The earliest atmosphere was composed of mostly hydrogen and helium. which are very light, and we do not breathe very well. Our atmosphere today is mostly nitrogen and oxygen. It's like 70-something% nitrogen, 20-something% oxygen, almost 30%. But yeah, that's not something that would do very well for us. And hydrogen is extremely flammable, so it also would have been a very volatile atmosphere. These gases, they say, were too light for the planet to retain. Many scientists think that the solar wind, charged particles from the surface of the sun, carried the young atmosphere away. It just basically blew the hydrogen and the helium away, which is something that happens in space. We believe that Mercury, the closest planet to the sun, used to have an atmosphere, but obviously it's so close to the sun it blew away. Mars's atmosphere blew away. It used to have an atmosphere. Now, Mars's atmosphere blew away from the same process as our hydrogen and helium, but one of the reasons is Mars used to have a magnetic field. Like we have a magnetic field. You can take a compass out, it'll point towards the North Pole or the South Pole, depending on what kind of compass you have. But Mars, it eventually got cold and its plate tectonics stopped. It doesn't have like a hot molten core, kind of like ours does with the same dynamics. And so it lost its magnetic field, which kind of exposed it to those solar rays more than Earth did, which is why Mars lost its atmosphere. So we used to have a bunch of hydrogen and helium. It all kind of went away. And actually, hydrogen and helium is so small anyways. Even today, like when we build pressure vessels, it's extremely hard for us to build a tank that will hold hydrogen and helium perfectly. There's always some sort of really tiny hole that they're escaping out of, and so it's hard to keep hydrogen and helium around. They're really easy to lose. So many scientists propose that the first atmosphere developed from the release of gases of volcanoes, which is why it wasn't very good for us. You don't want to go and breathe in volcanic smoke and gas. It's not going to be super great. The early atmosphere would have contained mostly hydrogen and large amounts of water vapor, carbon dioxide, and hydrogen sulfide. So know that carbon dioxide is a greenhouse gas, and so that's going to contribute to the heat and volatility of the early Earth, the young Earth. And then hydrogen sulfide is one of the things that comes out of volcanoes. So this is like a poisonous gas. You wouldn't be able to breathe that very well. Everybody keep their heads up. I'll turn the light on.
No.
Yes, lights on. Everybody stay awake. Come on. I need to have I got an air horn in the closet. I need to blow it every once in a while.
Yes.
So make me bring out the air horn.
Yes.
Put your mask up. All the way down under your chin. What's wrong with you?
Hey, breathe.
Yeah, you can. They just did scientific paper and they said that you can breathe. Mask doesn't decrease your oxygen intake at all. You got to work a little bit harder too, but that's like literally part of training for some athletes. So just deal with it. If you're gonna go play a game in Mile High Stadium, you got to work on breathing a little bit better. So wear your mask in public.
Aren't you breathing in like a little bit of carbon dioxide though?
Not much. You're always breathing in a little bit of carbon dioxide. Every time you take a breath, part of your breath stays in your mouth, so you're getting a little bit of it. Yeah. And see, that's a good. You got good seal on your mask, at least a little bit, because if it goes in and comes out while you breathe, it means you're actually filtering some of the stuff, and it's not just like blowing out the sides like some of y'all with your super loose masks. All right. So it's hard to read now, but all y'all better stay awake. So we're talking about the early atmosphere. It had a lot of carbon dioxide, a lot of hydrogen sulfide. It also would have contained nitrogen, small amounts of nitrogen, which is what we mostly have today, and carbon monoxide, which is a deadly gas again. Even just a little carbon monoxide in your house can be pretty bad for you. Methane, which is like rocket fuel, and other gases. The Mars rocket they're building down in South Texas actually runs on methane. So not super great early atmosphere. Like they said, they think it was blown off planet by a catastrophic. Oh, now they get into the Mars-sized impact. So they think that this other early atmosphere that wasn't just hydrogen and helium, but had all these other things, was blown off the planet by that huge Mars-sized collision that eventually formed the moon about 4.5 billion years ago. So this was roughly like, a couple 100 million years after the Earth actually started to solidify and form. Let's see. About 4 billion years ago, so roughly like almost a billion years or 3/4 of a billion years into the Earth's history, they think that the composition of the atmosphere changed again. The planet was still in the process of cooling. Volcanic activity at the planet's surface expelled a variety of gases into the atmosphere, primarily water vapor, carbon dioxide, hydrogen sulfide, and trace amounts of nitrogen, carbon monoxide, methane, and ammonia, which is kind of similar to what we had before, but a little bit different and probably different ratios. Many of the gases reacted with the minerals on land, dissolved into the ocean, and the gases that did not react began to accumulate and form Earth's secondary atmosphere or second atmosphere. The sun's light broke down ammonia from the volcanoes, and nitrogen was released slowly with buildup in the air. And that's the thing about nitrogen. Nitrogen isn't very reactive. It's kind of like an inert gas. It's not as inert as like the noble gases that don't combine with really anything. But nitrogen isn't extremely volatile. It doesn't easily combine with other things. And so it just kind of sits there in the atmosphere, which is why literally every breath you take is like 70-something% nitrogen. And our bodies don't really do a whole lot with it. We just breathe it in, breathe it back out. It's not that big of a deal. What we're more concerned with is the oxygen inside and how much of that we get. So this second phase, while it didn't give us nitrogen right away, all the chemicals that they gave us started to combine with rocks, and it helped to build up our nitrogen levels slowly over time, which led to the atmosphere that we have today. So now they talk about the formation of the oceans. Early Earth was obviously very inhospitable, but eventually the composition of the early crust was similar to the molten material originating in the planet's interior, and it brought to the surface volcanic eruptions almost daily. What those volcanic eruptions brought to the surface was chemicals that eventually cooled and led to the oceans forming. So over time, you get your early crust. It gets remelted over and over and over again, with each episode of melting and cooling, the chemical composition of the crust began to change. Two types of crust emerge, continental and oceanic. So we start to build our continents, which are going to last for a very long time. They're still very similar to the continents that we have today. We don't have a lot of reason to believe that they've changed because we can still find rocks that are really, really old, like we talked about. And just because of the density, if they're less dense than literally everything else, they're not going to be pushed down. They're not going to be melted back into the mantle. They're going to be kind of reused. Everybody make sure that you're awake. See y'all front here. See y'all and you back there. Those eyes are getting really sleepy. Yeah, look around like I'm not talking to you. Yeah. And all the people on YouTube can hear you.
All the two people.
Yeah, all the 2 people that will be watching this on YouTube. Or maybe some creep that wants to put like a bad link in the comment section. I had to close all my comments out. Yeah, I had to. I got all the comments closed now on my YouTube channel. So, yeah, I don't need y'all getting anybody in trouble or getting yourselves in trouble commenting on YouTube. Huh?
An example of a
Well, I don't think we can get our.
Oh, it would have definitely given you a
You can't
virus,
even comment.
like for
Oh,
sure.
that.
Yeah.
You can't even comment from the
That's a bad one.
Oh, can you not? Well, I've had a couple comments from students. I guess maybe from your your personal accounts. But anyways, listen, they emails me whenever I get comments. So
No, but how did you find it? How did you know that?
oh, you can tell. Like you can tell. Trust me, it was a bad link. It definitely 100% would have given you a virus. Yeah. Yeah, if you don't know yet to know what's going to give you a virus and what's not going to give you a virus, your computer probably has viruses. I'm just saying. You just get used to things. So, huh? No, we're just lecturing. You just gotta listen. That's your assignment. Stay awake and listen to me talk. Yeah. It's one of those days. So, let's see. They talk about the early crust. They talk about the volcanic eruptions. Notice how light the continental crust is. 2.7 grams per centimeters cube. Remember the core was like 13.5. So the continental crust is literally so light that it doesn't really matter what you do, what it smashes into. It's not going to be pushed down. It's not going to be remelted. It's just going to float along the surface and kind of hang out essentially until something really bad happens, which hopefully it doesn't. So when we get to Earth's oceans, they formed when the continents began to separate or rift apart. When this happened, material from Earth's molten interior rose to the surface, cooled, producing the oceanic crust. As the process continued, water condensed out of the atmosphere. So some of those things that were getting put out was a lot of hydrogen, a lot of oxygen. It formed to form your water vapor. And eventually, as the planet cooled enough, just like we have with clouds sometimes, your water vapor condenses, it starts to rain, and we start to get our first pools, our first lakes, and our first oceans. So as it rained, it flooded the rifted areas in between the continents, and we started to get our first oceans ever. That water gets evaporated, re-rained down, and it just happens, it starts the water cycle over and over again, just like the water cycle we have today. And they're basically saying as more oceanic crust was added, the rifted continents were pushed further apart, and the ocean basins got bigger and bigger and bigger. Now, does anybody know like what the total percentage of Earth's surface is for water?
70.
I think it's like 70-something%. Yeah. It's mostly water. And when we talk about Pangea, with like all the continents together in one place, know that while it looks cool on the map, literally like the rest of the world is all water. So like more than half of the other globe is just one gigantic ocean that never ends. And so that's pretty interesting. So this is actually how it happens, and we're actually covering this in dual credit geology right now. So you have magma that comes up, it pushes up on the crust, gravity is pulling down, there's only one way for it to go, downhill in opposite directions, and so it's going to start to rip this apart. The oceanic crust is thinner than the continental crust, so actually as it starts to rip it apart, it gets thinned out in the middle, which allows your water to settle down in those basins and kind of all pool and collect together, which gives you a nice ocean. So now a lack of oxygen. And so we have water vapor in the air, which has oxygen in it, but it's not free oxygen. In the same way that, it's H2O with oxygen in it, but you can't go underwater and just breathe it because that oxygen's not available for you to breathe. And so water vapor in the air is part of it, but they don't have any really free oxygen for life forms to start to breathe and to develop. And it actually took, I don't know how they're going to do this. Yes, it actually took life on Earth to happen before we actually got oxygen for most of the life to develop as it is today. Most of the life that we have today relies on oxygen. That's one of the things we look for when we look for alien life. But it says almost all life on the planet depends on oxygen, but the early atmosphere didn't really have any for us to breathe. So it's important to understand how this element became so abundant in today's atmosphere. Again, it's like 20-something% oxygen. So we have a lot of oxygen in the atmosphere. Oxygen in the atmosphere can be linked to ancient blue-green algae, bacteria, which they call cyanobacteria. These organisms conducted photosynthesis, which you've all learned about photosynthesis in cells class. The photosynthesis is a product that they use to take in sunlight, to create energy, and to give themselves some oxygen. Lights are coming on. See all y'all dozing off. So the chemical reaction converts carbon dioxide, which we had plenty of in the atmosphere at that time. It's your greenhouse gas. It converts it from carbon dioxide and water to glucose, a simple sugar, and it produces a little bit of free oxygen. So that's one of the byproducts of it, is spitting out a little bit of oxygen, which is why trees are good for us, because they take in the sunlight and they produce more oxygen. As the population of bacteria increased, the concentration of oxygen in the atmosphere slowly began to increase. And still at this point, they have a whole bunch of carbon dioxide. The water is there to help them kind of survive the radiation, survive the high temperatures, and they just flourish for a long time, just creating a whole bunch of oxygen. So they're talking about it increasing. The blue-green bacteria basically formed these big mound-like structures called stromatolites. You can find these today. I think there's living ones today, but you can go out and find these in the rock record. I've seen stromatolites on geology field trips. It's actually pretty interesting. They're just this kind of like, it looks like somebody took a bunch of little carpets and kind of piled them up, and then it all just gets stuck in the rock record. And so it almost looks like a big like mushroom pile. It kind of has this look to it. It just layers upon layers, and these big kind of mounds. And you'll see them in a overall bigger rock because they have to be preserved some way. But stromatolites are actually pretty interesting, and they're one of the oldest, like larger organisms that we can actually find in the rock record. There's no bones or hard parts or anything. They're just kind of there. Make sure you wait. Step on him. You drink some coffee or something, man. Get some Red Bull going on. Right into the veins. Yeah. He's studying. I got a stitch that's out. Yeah, I get it. I understand. But just refocus back up here. Don't look at your sleeve no more. Terry's trying to help you out here. As these blue-green bacteria form the stromatolites, they use this free oxygen they produce, and it reacted with other elements in the ocean, like iron, which started to produce iron-rich materials like your rusted kind of look in a lot of the rocks that we have. So hematite is very red. It's almost like a blood red kind of rock. In fact, it's named for, hemoglobin, which is in your blood, the red blood cells. Hemoglobin, I don't know, ask your biology teacher. Hemoglobin's in your blood. It's like isn't it? Y'all know, yeah, come on. Yeah, there you go. Magnetite, which is a magnetic rock, and we might actually see these when we get to the rock section. We probably should have already done the rock section, but I'm just going through the order of Discovery Education. And a couple other minerals that have iron and oxygen in them. As the concentration of iron in the oceans diminished, the oceans began to release free oxygen into the atmosphere, which kind of helped along the process and give us even more oxygen. At first, they're saying the oxygen did not accumulate. Instead, it also reacted with other elements on land. Oxygen is very reactive, which is why, what do you need to burn anything? You need oxygen. If you don't have any oxygen, your fire's not going to burn, which is why they tell you to like smother out fires. Like if you have a campfire or something, you cover it with dirt or sand, and you just keep it from getting oxygen. It's also why we have a fire blanket over there. You throw the blanket down on something, it keeps oxygen from getting to it. The fire goes out.
Or if you need to take a nap.
No, that's not a comfortable. It's like a wool blanket. It's probably it probably would be itchy. It's meant to save your life, not to give you a nap. Some of y'all need to take some naps overnight before you come to school, so you stay awake.
We do. They get us. We have to be at school at 7:30 something.
I have to be here too.
Who makes these rules?
Hey, you should be on my side.
No.
Yeah.
Yeah. How long do you think I'd keep this job if I was just like falling asleep while I was doing the lecture?
You think we're gonna snitch?
No one's a
Yeah,
snitch.
Whatever. Yeah. No,
You-
listen. You say that, and I understand what you're saying. If I fell asleep in the middle of a lecture, everyone in school would be talking about it before lunch. Y'all can't deny that. You cannot deny that. You would just tell everybody, Mr. Bailey fell asleep today. And he's like, right in the middle of a sentence, his eyes just shut, and his head fell over, and he kind of like bumped his head. No, like y'all would literally record me and put me on TikTok. You know you would.
You fell asleep. We fall asleep too.
No. Some people would fall asleep too. But no, I would be on the internet before the period was over for sure. You know I'm right, right? Yeah, y'all absolutely would. So look, back on track. So we don't have to do this tomorrow. You can just do an assignment. So they're talking about the oxygen building up. They say at first it didn't really build up too much because it's so reactive. It reacted with other minerals and rocks that were in the ground. But at a certain point, you get enough where it does start to build up in the atmosphere, and we start to get towards the atmosphere that we have. So about 2.5 billion years ago, which is still not too long ago. Still pretty early. This is still going to be Precambrian, which we'll learn. No, we learned about that already. It's still going to be Precambrian before we get a lot of life on. But around then, you still only have about 1% oxygen in the atmosphere. By 2 billion years ago, the concentration began to increase. And by 700 million years ago, probably right around the beginning of the Cambrian era or in the Cambrian era, it had increased to 20%, which is really nice. That's a good oxygen level. You can start to have things breathing oxygen and getting more and more complex as a life form. So the oxygen built up, you get more ozone. Does anybody know what ozone is?
The layer.
Yeah, it is an ozone layer. And it's actually O3. So instead of O2 that we breathe, ozone has 3 oxygens bonded together, and that's what forms that ozone layer up in the atmosphere, which is actually good. It helps protect us, huh?
What happens if we breathe that?
Yeah,
It's not good for you. Your oxygen your lungs don't take it in. Your body doesn't process it the same way.
Oxygen.
That'd be cool. Like grew another layer.
It is extra oxygen, but it doesn't work the same chemically. It's a different chemical. So it would not be good if you breathed it. So listen. The addition of ozone in the atmosphere blocked some of the sun's radiation, which helped us live a little bit longer. The creation of the ozone layer allowed more terrestrial life in the Earth's geosphere to survive and evolve and become more and more complex, which is good because that led to us happening. We're complex beings with complex thoughts.
Smart.
Yeah, we're real smart. So, nice. That's the end of the page. The buildup of oxygen. So basically, this entire section is about Earth's history, how we went from a molten globe to we started to form oceans, we started to form continents, we started to get an atmosphere that's more hospitable to life on Earth, and that we eventually could breathe and eventually get to the point where we have the atmosphere that we do today. So tomorrow, how much time we have left in class? We're not going to do it. I'm just wondering.
8 minutes.
8 minutes. Nice. Perfect. So tomorrow we will. What is tomorrow? Wednesday?
Seven.
We'll see. It's not the 7th or Saturday. Both of y'all wrong.
Wednesday.
Tomorrow we'll either do the multiple choice one or we'll do the constructive response one. We'll figure it out. Yeah, I know you say that, but some of y'all need to be making sure that you take your time on the multiple choice. And if you get a really bad grade on it, you can come in during activity period, and I will let you retake it. I have a couple students who come in every once in a while. They're like, "Hey, I did bad on that quiz, or I did bad on that assignment. Let me retake it." No, they just want to pass and be able to graduate. We're all just trying to get y'all out of here so we don't have to hear you make weird noises anymore. Me? No. Sometimes 7th period though, that's my off period. Sometimes like it's hard. I'm sitting here at my desk trying to get stuff done, and my eyes, just like him early, eyes are getting closed, heads nodding. But I always got the bell to wake me up. So, but I don't think I've fallen asleep yet, but I do get sleepy. All right. So online people, if you watch to the end, congratulations. Maybe one day, like I will go and like hide a $20 bill somewhere around school, like on the outside of the school, and I'll tell them like where to find it, like a treasure hunt, and just if anybody ever does it, they'll find the money.
For real.
How do you know? All my views are about to go up. No. I had a professor that he said that when he wrote his master's thesis in college, he put like I don't know, like a $5 bill or something. It was probably more money back then, but he put a $5 bill like in his master's thesis book, and basically every time he goes back to the school, he goes and checks his book to see if the $5 bill's gone, because he's like, if you read this, you deserve $5 at least. Like it's not an exciting book. But that also tells him whether anybody's ever read the book or not. Because every time he goes back and the $5 is still there, he's like, "Oh, they haven't read it yet." I don't know. I think it's kind of fun because like I don't have any expectations that anybody ever reads my master's thesis. I would be surprised if they ever have.
I'll read it.
Just put like.
What do we got? Like just a couple
You
minutes?
put a Chick-fil-A or a Starbucks card, you know how many people gonna
Just like a
Fourth period.
gift card code.
Better be quick.
Yeah.
I will be quick. I will sprint.
You
All right, so online people, don't come look for money. I haven't hit it yet, but maybe one day. I don't know. We'll see. We'll see what happens. Y'all have a nice day.